This is an introduction guide to pipelining architecture from MIPS instructions. The target audience for this video is anyone who is being introduced to pipelining architecture for the first time and has a background knowledge with some computer assembly language. So what is pipelining? Pipelining is a process in which a computer instruction can be executed before the previous instruction has been completed. Each instruction is placed in a sequence of modules or stages. Only one instruction can be in a stage during a cycle, and the amount of stages for this architecture is 5. To understand the big picture of pipelining and what it does for computer instructions, let's look at a quick real-world application. Let's say a doctor's office is set up with pipelining architecture, and the doctor's patients are considered to be pipeline instructions. First, a patient must schedule an appointment with the doctor. Next, the patient will go to the waiting room. Following the waiting room, the patient will be checked up by the doctor. The last stage is for the patient to pay for the doctor's visit. Once one patient has made an appointment to see the doctor, another patient can make an appointment right after. The doctor can only see one patient at a time, so each patient has to wait one cycle before they can see the doctor. This process can continue for however many patients the doctor has. Continuing with this example, an important point to make is that the pipelining rate, or the time to visit the doctor, is limited by the slowest stage. That is, if it takes 5 minutes to make an appointment, 10 minutes to wait for the doctor, 20 minutes for the doctor's checkup, and 5 minutes to pay, then regardless of which stage the patient is in, it'll take 20 minutes to move to the next stage. So, if it takes longer for each patient to get through the doctor's office, then why would we want to use pipelining? Well, pipelining is not meant to help the latency of a single instruction, but to increase the throughput of an entire workload. This top diagram shows that it takes 40 minutes for a patient to complete a doctor's visit if the doctor's office was using a single cycle path. The bottom diagram shows how it takes 80 minutes for a patient to complete a doctor's visit. However, we can see that pipelining allows more patients to be seen by the doctor through the course of a workday. This type of utilization for computers is essential. Pipelining architecture from MIPS instructions uses 5 stages: instruction fetch, instruction decode, execute, memory, and write back. Some instructions, however, don't use all 5 stages. Branch will only use fetch, decode, and execute. R-type instructions like add and subtract will use fetch, decode, execute, and write back. Store word uses fetch, decode, execute, and memory, and then load word uses all 5 stages. This diagram shows a breakdown of the architecture used for pipelining. This architecture allows specific instructions to be processed by each stage or to skip certain stages if needed. It is important to note that this diagram is incomplete and is used just for a basic understanding. Now that we understand the big picture of pipelining, there are a few requirements that instructions must come across. Instruction dependencies is where data from one instruction depends upon data created by a previous instruction. In this example, the value of register 2 and register 1 are added and stored into register 3. The next instruction needs the data from register 3 to complete its execution. Instruction 2 depends on the first instruction to complete its execution before it can continue. This is considered a data dependency. Data dependencies can become data hazards. This occurs when an instruction depends on the result of a previous instruction, but the previous instruction hasn't produced the data yet. In this example, register 1 and register 3 are subtracted, and the results is stored into register 2. The data stored in register 2 is needed in the next instruction. However, if we look at the pipeline stages, the value stored in register 2 is not finished in time for the next instruction. This is considered to be a data hazard. There is a workaround or a solution to the problem of hazards. Pipeline forwarding allows the passing of data from one pipeline directly to another to eliminate intermediate storage. Forwarding can take place in the EX-MEM pipeline, which is between the execute and memory stages. Forwarding can also take place in the MEM-WB pipeline, which is between the memory and write-back stages. This will remove data hazards. To conclude what we've learned, let's look at one complete example. We are asked to examine the following instruction and identify the dependencies, the hazards, and then draw a multiple clock cycle pipeline diagram to support our answer. One approach to this problem is to first identify all the dependencies. We see that register 2 is used in instruction 1 and instruction 2. So this is our first dependency. Then register 4 is used in instruction 2 and 3. So we have two dependencies. Sometimes it can be difficult to visualize if a dependency is a data hazard, so the next step should be to draw out the clock cycle diagram. From the diagram, we see that the add instruction finishes its execution of register 2 in the EX stage. With EX MEM forwarding, it can be sent directly to the EX stage of the instruction 2. This means that there are no hazards with this dependency. For the next cycle diagram, we see that the load word finishes with register 4 in the MEM stage. Load word needs the MEM stage to complete its instruction. Instruction 3 needs register 4 before it is ready. Even with MEM-WB forwarding, we can see that the third instruction is one cycle ahead. So what do we do? What has to occur is a cycle stall for the third instruction. Once a stall has been implemented, we can see that the MEM-WB forwarding can do its job and send over the data from register 4 to the third instruction, right when it's needed. So the dependency from instruction 1 to 2 is solved with the EX MEM forwarding, and the data hazard from instruction 2 to 3 is solved by one stall, and then the dependency from instruction 2 to 3 is solved from the MEM-WB forwarding. This concludes the Introduction Guide to Pipelining for MIPS instructions. It is important to note that there are many exceptions, details, and other hazards specific to MIPS instructions that this guide did not cover. However, I hope this video provided a good foundation for viewers when learning more about pipelining architecture.